Hi guys, this is Dr. K. We're going to look at pH calculations for weak bases. Weak bases come in two types. They can be the conjugate bases of weak acids, and they can also be amines. So let's talk about the structures. The conjugate bases of weak acids are weak acids, for example, like HF or acetic acid. So hydrofluoric acid, HF, produces a weak base on ionization, which would be F-. In a problem, we would see this as sodium fluoride, for example. You almost never see in a problem just fluoride ion by itself, because when you have an anion, you have to have a cation that goes along with it. For practical purposes in doing the calculations, this is almost always a spectator ion and can be ignored. For acetic acid, we would write that as in its carboxylic acid form is CH3COO-, but this comes from acetic acid, CH3COOH. Again, this negative charge has to be offset by some type of cation, so it could, for example, be a sodium ion, potassium ion, something like that. Amine bases are structured around the Lewis structure for ammonia. Now, ammonia's Lewis structure looks like this. It has four bonds, or four groups, a lone pair, and three bonds. In ammonia, these three bonds are connected to hydrogens. In the amine bases, we typically have one of these groups substituted by another type of atom. For example, methylamine, CH3 is the functional group, a methyl functional group. Or dimethylamine, which would have two methyl groups on it. There would be also a triethylamine, but if you had a tetramethylammoniamine, this would end up being a cation. You would have a group attached to this lone pair. Now, amine bases need this lone pair to act as a proton acceptor. And if it's occupied by a fourth group, another methyl group, for example, that in central nitrogen takes on a positive charge, but more importantly for the discussions of acids and bases, it can't act as a base anymore because the lone pair isn't there to accept the proton. So let's look how we generalize acid-base reactions for weak bases. So to describe the acid-base properties of weak bases, we're going to use the Bronsted-Lowry definition. And remember, the Bronsted-Lowry definition talks about proton donors and proton acceptors. So let's say we have the conjugate base of a weak acid. It's going to have a negative charge. It's going to accept a hydrogen ion from the water molecule. This leaves water in the form of hydroxide. That's where we get our elevated pH in the basic solution. And we get the acid of the conjugate base. If it's a neutral base, for example, an amine base, one of the distinctions between conjugate bases of weak acids and amine bases is that the base in an amine is neutral. It acts as, again, the proton acceptor, and as a result, the water forms hydroxide ion and Hb+. You'll notice in form, the only ways that these are different is which atoms or molecules carry a charge. Otherwise, they're treated exactly the same way. So let's do an example. Let's calculate the pH of a 0.14 molar solution of NaCHO2. Now, you may not know that CHO2 was formate ion, so how are you going to deal with this when you get it on a test? Well, first of all, one of the things you have to recognize is that because it has sodium in the formula, that's this, it's probably the conjugate base of a weak acid. So now what you're going to do is you're going to go to your tables and you're going to look for the CHO2- ion And if you look in the back of the textbook, what you find is that formic acid is HCHO2 with a Ka value of 1.8 times 10 to the minus fourth. So going back to our problem, we know that Ka is 1.8 times 10 to the minus 4. But this is a base. So what we need to do is you have to remember that Kw is equal to Ka times Kb, so that you could calculate Kb, which is what you need for this problem, as Kw divided by Ka. When you do this, what you find is that Kb is 5.55 times 10 to the minus 11, and the 5 is repeating. We have two significant figures. So now what we do is we have to set up our ice table. So now we have to start with our reaction. We know we're dealing with the conjugate base of the weak acid formate, so I'll go ahead and start though with A minus. So we start with A minus plus H2O is in equilibrium. Again, Bronsted-Lowry definition, I'll get OH minus plus the acid of that conjugate base. And then I'll have initial of change, and I'll have equilibrium. And go ahead and draw my lines. Kind of messy, but I think you get the idea. And then for A minus, I'll start off with 0.14 molar. Water, pure liquid, we'll leave that out. OH and HA, we'll just assume those are 0 to start with. We know it's going to go to the right because I don't have any weak acid or hydroxide, and I'll get plus X on the right. So I have 0.14 minus X, X, and X. Now, plug that into my Ka expression, or Kb expression. I know that Kb is equal to the concentration of OH minus times HA divided by the concentration of A minus. Plugging values in, I find that it's X times X over 0.14 minus X, and that's all equal to 5.55 times 10 to the minus 11. I used Wolfram alpha to solve this. I get X is equal to 1.18 times 10 to the minus 6. Now remember what this is. This is actually the hydroxide ion concentration, and I am looking for pH. So I calculate pH first by calculating the pOH. I know pOH is equal to negative log of hydronium, or hydroxide. That's the X value, and so this comes out to be 5.928, 2 sig figs in my answer. So the pH is equal to 14 minus pOH, one of those valuable relationships that you should know, and you end up getting pH is equal to 8.07. So there you go. That's how you would calculate using the conjugate base of a weak acid. The value looks reasonable. It's a weak base. We'd expect the pH to be a little bit higher than 7. In this case, the pH happens to be 8.0. So let's look at our next example. Example 2 is we have an amine base. So we're going to calculate the pH of a 0.27 molar concentration solution of methylamine. So methylamine, we're just going to call that B. B plus water. It's going to be in equilibrium with OH minus, this is the Bronsted-Lowry again definition, plus HB plus. This would be the methylammonium ion in this particular instance. We'll set up our ice table. And we'll have initial we'll have change, and we'll have equilibrium. Again, we'll ignore the water because it is a pure liquid. And we'll fill this ice table out as 0.27. This will be minus x and 0.27 minus x. These will start off as 0, and so they'll both change to x, and so I have x and x. And you'll notice the form of this reaction is exactly the same as the previous problem example. We know that Kb is going to be equal to x times x over 0.27 minus x. Now, what's the weak base ionization constant? What is the value for Kb? So what we do is we go back over to our textbook, and you'll notice that this whole table is for dissociation constants of weak acids. Then there's some metal ions, and so what we'll do is we'll actually go to the next page, and what you'll see is dissociation constants for bases. And if you look, methylamine, let's go down here under M, methylamine is right here. And what I find useful is that these values are listed both alphabetically and by formula, and so you can see that the Kb value for this reaction is 4.4 times 10 to the minus 4. This is a little bit easier than working with the conjugate base of a weak acid because you don't have to go through the intermediate step of calculating Kb for the problem. So let's go back. So here we are back at the problem. We know that Kb, this is equal to 4.4 times 10 to the minus 4. And again, I just went to Wolfram alpha. You could solve this using a quadratic equation or the solver in your calculator. And what you find is that x, again, which is the OH minus concentration, is 0.01068 molar. This means that the POH is equal to negative log of 0.01068. That's going to be equal to 1.97, so that the pH is equal to 14 minus 1.97, or 12.03. So I hope that helped you if you needed the help. You can ask me questions in class.